Hey everyone, on this lesson we are going to solve the problem 5 on the collection of problems about reductions of the Halting problem. So this problem 5 says reduce the set and the problem complementary k to the set of natural numbers such that the program codified by them computes the identity function. Okay, so to prove that such set, this one, is not semi-decidable. So we know that the problem complementary k is a not semi-decidable problem. So if we reduce this problem complementary k to another problem, then we will prove that this other problem will also, not be semi-decidable. So we need to give the reduction function, when we are demonstrating and presenting a reduction, we always need to give the reduction function. Although the most important part is not the reduction function, but how we prove that the reduction is correct, right? So we already saw this, and basically if we have a problem A and we have another problem B, and this is also generalized and true for sets. Okay, we can have a set A and set B. So if we want to reduce the problem A to the problem B, as it's shown in here, then we need to prove that for each element, for instance, x, that belongs to the problem A, after applying the reduction function, this element will also belong to the problem B. And if we have an element x that does not belong to A, after applying this same reduction function, then the element x won't belong to B neither. And this is the main part on any reduction, mainly when we are proving that a reduction is correct. So we need to give the reduction function for this problem so that we can come from the complementary k problem to this new one that we will call the problem P. So keep in mind that the idea of this problem P is basically each element P, each natural number P, such that for each input that we may have on the Turing machine P, the output of this Turing machine is going to be the same as the input. So if my input is 5, the output is going to be 5. If my input is 7, then the output is going to be 7. So it is basically all the Turing machines that are the identity function. So let's first remember what is the problem complementary k. We have seen along these lessons on this section that basically we have the problem k, which is basically the set of programs that stop with input themselves. So basically the problem complementary k, what will this problem be? Well, it is basically all the programs that do not stop with input themselves. Remember that this arrow pointing to the top means that the program don't stop. This program does not stop. So we have that the set complementary k is all elements x such that the Turing machine x with input itself, with the same input x, will not stop. This will not stop. It will going to be running forever. So this is our set, the set complementary k. And then we have to reduce this set, this problem, to this new one, the problem P, which is this problem in here. So how can we do that? Well, we have to ensure basically that if we have an element, this element x, that belongs to the set complementary k, it means that the program, the Turing machine x with input x will not stop by definition of the complementary k problem, but we need to apply the reduction function. So at the end, this same element needs to belong to P. So basically the output, of the Turing machine P with input y needs to be y. And in the same way, if we have an element that doesn't belong to the set complementary k, then after applying a series of transformations, this element x, must not belong to P. So basically the output, of the Turing machine P with input y, in this case will not be y, it will be different. Keep in mind that the idea is that there is at least one element such that the output is different. Keep in mind that we have here the universal quantifier, okay, and then we have to negate this, so we have the existence. In other words, the set complementary P, okay, is basically all elements P such that there exists some Y, okay, such that the Turing machine P with input Y is not Y. So this is the complementary of P. Keep in mind that if we have an element that basically doesn't belong to P, then this element belongs to the set complementary P, okay, by definition of sets. So this is the whole idea that we need to demonstrate in here. So we need to give a reduction function that ensures that if I have an element that belongs to this set, it will also belong to P. And if I have an element that does not belong to this set, it won't also, okay, belong to P. So let's give now this reduction function. So let's give the reduction function f, okay, with input y. So the input of this function is y. So basically the main idea of this reduction is that if the element doesn't belong to this set, okay, or it won't belong to P, and if it does belong to this set, it will belong to P. So how can we ensure that the element belongs to this set complementary K? Well, basically, we can give that if the element, okay, that we have, the Turing machine X with input X doesn't stop with the input steps, it means that belongs to this set. So basically, we will have a conditional if here. So basically, what we're doing now is to ensure that this element belongs to this set, okay? So if the Turing machine X with input X doesn't stop, so basically the arrow goes to the top because it runs forever in input steps. So basically here in Y steps, keep in mind that Y is the input, okay? So if this happens, then it means that the element, okay, this is the same as saying that the element belongs to the set complementary K, right? So this also means that this element needs to belong to P. So how can we ensure that this Turing machine M, okay, will have the output Y? Well, if this happens, we can just say output Y. So here we will just write the instruction output or return, okay, Y, like so. And we end the brace. So this is mainly the reduction function. With this is enough. So many students may ask now, okay, with this you ensure that the positive case, if you have an element that belongs to the set complementary K, so if this condition is met, then you will output Y, which is this output here. So the element X will also belong to P, okay? Now what happens in the negative case? What if my element X does not belong to the set complementary K? So what if this condition is not met? So this is also, okay, correct. Why? Just consider, if we have an element X that doesn't belong to K, complementary, it means that this condition is not met. Okay, if this condition is not satisfied, we will never go to this instruction. Okay, we will never execute this instruction. So basically the output will not be Y, it will be a output different from Y. So this element will also not belong to P, okay, like so. So with this reduction function, we ensure that this happens. You can also say that in the negative case, in the case that this happens, basically this is not satisfied, you could write here else, and then write an infinite loop like while 1, okay, like so. However, this is not necessary because it is enough to not return Y. So since the output is not Y when this is the negative case, okay, then this element also, okay, does not belong to P. So we satisfy the condition. So this is the reduction function that we need. Let's formalize now this reduction function in code. So this is our reduction function, right? So let's consider now the case that the element X belongs to complementary k, okay, then is because this condition is met if the Turing machine X with input X does not stop with input steps. Okay, here is just notation, but it's the same idea as this conditional in here, okay, that we have. If the Turing machine X, okay, with input X does not stop with input steps, and here we write not to formalize that it don't, okay, it does not stop with these input steps, then it means that this is true. So wait, let's just comment this here. So what we will do in this case is basically output y. Okay, so now we guarantee with this output, this is very important. When we put the output y, we guarantee that x belongs to p. Okay, like so. And let's end the brace. Now, otherwise, this is the else case. Okay, x does not belong to the set complementary k. Then the output is not y. So x does not belong to p neither. Okay, so this is the reduction function that we need. Is the only reduction function that exists? Okay, no, there are more. Okay, for instance, we can do the same in the reverse thinking and reasoning, but to achieve the same result. For instance, another possible way of doing this is we could say, okay, input y, imagine that this is the other reduction function. So we can just say, if the Turing machine X with input X stops in input steps, okay, it means that this element X does not belong to K. So in this case, how can we verify that the element X will not belong to P? Well, we can just reject, or we can also write here, if you want, infinite loop. Okay, all those are solutions, but reject is okay also. Okay, so if the element X does not belong to K, because of this condition, because we know, in this case, complementary K, like so, okay, since we know that the Turing machine X with input X stops, okay, it counts with input steps, then the element does not belong to complementary K, it belongs to K, right? So then we need to make sure that the output is not Y, so it also does not belong to P, so we just write reject, so X does not belong to P. Otherwise, okay, otherwise, it means that X belongs to complementary K, and here, and then we know for sure that the element will also belong to P, because here we have the output Y, so X also belongs to P. So there are, here we have two ways of doing this reduction function, the first option or the second. Both of them are correct, okay? We remind the student that he can download the solution to this problem as well as the problem statement on the downloadable documents of this lesson. On the next lessons, we will keep working with reductions and solve more problems.